Up to this point, we've been talking about intermolecular forces and been relating it to the boiling point as kind of a measure for the strength of intermolecular forces. And the logical extension in this conversation is to talk not only about boiling point, but about all phase changes, going from solid to liquid, liquid to gas, or solid to gas, etc. And each of these processes involve energy in some form. And so we can create this diagram here to illustrate these processes on an energy axis. Now there's a few new terms in terms of phase changes that we need to specify. So I think we're fairly familiar with boiling, but that is given the term vaporization. That's fairly straightforward. Melting we use to go from a solid to a liquid, but in chemistry often melting is given the term fusion. And so the enthalpy, delta H of fusion, or heat of fusion, is really just the energy or the heat involved in melting. Condensation and freezing we're fairly familiar with, but we may not know that going directly from a solid to a gas can be done. That's known as sublimation, and the reverse process is known as deposition. Now, the lines shown in blue indicate endothermic processes. Those are ones that require heat or energy added to the system. And red are shown as exothermic processes, or ones that would give off heat or energy. Now, for water specifically, we can look at melting and say that the delta H of fusion, or the heat of fusion, is 6.01 kilojoules. Now, we can extend this a little bit and say that delta H of vaporization, this is the heat of vaporization, would be the amount of enthalpy or the amount of heat associated with boiling. And we'll notice if we do this for water that going from liquid water to gas is 40.7 kilojoules per mole. And it's important to note here that the heat of vaporization is much larger than the heat of fusion. So both processes here are endothermic. They both require heat to be input into the system. But why exactly is the heat of vaporization so much larger than the heat of fusion? Well, what we're doing, consider the aspects of what's occurring when we're going from a solid to a liquid and a liquid to a gas. When we're going from a solid to a liquid, we are disrupting some of the intermolecular interactions and increasing the freedom of motion or the energy of the system by turning that into some kinetic energy now in the form of motion. But the molecules are still right next to each other, even if they're freely moving now, and they still have many intermolecular interactions, attractions and repulsions with each other. However, when we go from a liquid to a gas, we are taking those molecules that are all right next to each other and have many intermolecular interactions, and we're separating them entirely from all of their neighbors, because in the gas phase, the molecules behave isolated. And so we're breaking all of the possible intermolecular interactions in order to separate and isolate those molecules. And that requires a lot of energy, much more than it requires to simply increase the degrees of freedom of the system. Now, in terms of the enthalpy of sublimation, this one is one that might be a little bit difficult for us to measure directly, but we can get it as simply the sum of the heat of fusion and heat of vaporization of the system, both of which are generally fairly easy to measure. Now, the reverse processes for any of these phase changes have the same enthalpy, just of opposite sign. Remember, if a reaction is drawn one way and it has an enthalpy with it, we can write it in reverse with just the opposite sign to the enthalpy. So the delta H of freezing is just minus the delta H of fusion. Heat of condensation is just minus the heat of vaporization. Heat of deposition is minus the heat of sublimation. Now we can look in a little bit more detail at these phase changes and what happens if we start, say, with solid water at a very cold temperature or some solid material, and then increase the temperature and progress through the various phase changes. what we will see is something like this that's known as a heating curve, where we have temperature on the y-axis and then the amount of heat added, which could be enthalpy or related to energy. And what we'll see is if we do this for water, what we notice is that we can start at point A at some in the solid form at as cold a temperature as we want to be, say -25 degrees Celsius. And we will see that the temperature of the system will increase as we add heat to that in a linear fashion until we hit the point where we start to melt. Now, when we begin to melt, we can add more and more heat to the system, but the temperature of the system will not change. So why does the temperature not change during melting? And then we see a similar case where the temperature does not change from 100 for a long time till we finally hit point E, and then it will begin to increase again. So what's going on here? Well, once we've increased the temperature of the system, that will increase linearly with input heat until we hit the phase change. But remember that phase changes are endothermic processes. They require heat. And so the heat that we input goes to the phase change. It goes to the process of converting liquid water into, or solid water into liquid water. And then once we increase the temperature of the liquid water up to boiling, then it goes into the liquid water to transform it into gaseous steam. So the energy or the heat that we input into the system goes to the phase change. Once we have completed the phase change, as we see at point C or point E, then we are entirely in the new phase, and any heat inputted will increase the temperature of that phase directly proportionally. So let's talk in a little bit more detail on the effects of temperature and pressure on phase changes and on the states of materials. So temperature, remember, is directly proportional to the kinetic energy. Remember, we used temperature and the kinetic energy to be able to calculate the speed of gas molecules. And the kinetic energy is directly proportional to motion, which is then directly proportional to intermolecular distance. So if we have a lot of kinetic energy, as in the gas form, then the molecules end up far away from each other. They zoom all over the place and become isolated. They escape in some fashion, unless we constrain them in some way. And so increasing the temperature, because we increase the kinetic energy and thus the amount of motion and the intermolecular distance, we go from a solid to a liquid, and then as we continue to increase the temperature, we go to a gas. That's fairly straightforward. We're pretty familiar with that. And if we do the opposite, if we decrease the temperature, we go from gas to liquid and liquid to solid, normally speaking. Pressure, on the other hand, pressure is not like directly proportional to the kinetic energy exactly, but it is directly proportional to the intermolecular distance. So the distance between molecules is dependent on the pressure of the system. If we increase the pressure, we force the molecules to be closer to each other. We decrease the intermolecular distance. So I guess pressure and intermolecular distance, I guess, are inversely proportional to each other. So increasing the pressure goes from gas to liquid to solid, and vice versa. Decreasing it goes from solid to liquid to gas. Now, there are two terms here that we should know: critical temperature and critical pressure. And those are best illustrated using an example. So if we take this cylinder here that has gas molecules in it, and then we press on the cylinder, we decrease the volume, we increase the pressure, then what we'll notice is a certain effect. So at 100 degrees Celsius, so at a certain temperature, the pressure that's required to perform a phase change, to condense water vapor to water liquid, is 1 atmosphere. So that's simply at 100 degrees Celsius as the boiling point. If we have 1 atmosphere of pressure, we've got an equilibrium between gas and liquid, and simply applying a small amount of pressure condenses that gas into liquid. However, if we increase the temperature beyond 100 degrees, then the pressure that's required to get back to the point where we can condense liquid goes up. It's 1.4 atmospheres. If I go up to 374 degrees Celsius, then the pressure required is all the way up at 217.7 atmospheres. Finally, as we increase the temperature further and further, eventually we hit some point where it doesn't matter how much I compress the cylinder, I will never be able to get to the point where I can form liquid water again. And that is known as the critical point. So the critical temperature is the highest temperature at which a distinct liquid phase can exist for a material. And the critical pressure is simply the pressure required to form a liquid at the critical temperature. So there are many critical temperatures and pressures. Each individual material has its own critical temperature and pressure, and the combination of those is the critical point. Nitrogen, for example, you can see its critical temperature and pressure is 122.1 Kelvin and 33.5 atmospheres. We'll notice as we go up this table or down this table that the temperature increases until we get all the way to water, and the pressure increases as well. So what we can define from this is that the greater the amount of intermolecular forces, the higher the critical pressure, temperature and pressure. If we have greater intermolecular interactions, then it's easier to form a liquid phase as we force those molecules together because they want to be together due to the intermolecular attractions. If there's essentially minimal intermolecular attractions, as in nitrogen, nonpolar, the only interactions there are dispersion forces, then there's really the temperature, the maximum temperature where you're going to be able to compress it enough to form a liquid is fairly low. 126.1 Kelvin, this is a very low value. However, as we increase and get more intermolecular attractions, finally hydrogen sulfide here would have some dipole-dipole interactions all the way up to water, which has dipole-dipole and hydrogen bonding. We see we have a much higher critical temperature and